Good afternoon. I'm Saritha Kumari, Assistant Professor, EEE Department, working in Institute of Aeronautical Engineering College, Dundigal, Hyderabad. Today, the topic is inductance problems on three-phase transmission line. So, again, the topic mapped to CO1, course outcome 1. So, before going into the problem, just for the transmission lines, the physical appearance, the transmission line, for an idea, how a single circuit line and a double circuit line. So, double circuit line means composite conductor. Okay. So, sorry, not composite conductor. Double circuit line means per phase there are two conductors. Per phase there are two conductors. So here, first single circuit transmission line with bundled conductors. So that means here you can see a single phase. This is a single phase transmission line, and it consisting of only one conductor for in the phase. So there is only one conductor. Single phase transmission line means the other one is a return line, that is a return path we say. So that means one conductor acts as a go conductor, the other one acts as a return conductor, and here, so this is this is the other line, and both are bundled conductors. And you can see the transmission line, how it looks like. So the transmission on the transmission tower, this is a transmission tower, one type of transmission tower, where the transmission lines are running from one place to another place like this. So which are placed on the insulators. So the transmission lines placed on the transmission towers, which are also called supporting towers, by using insulators. So these are the insulators, you can see. So about the insulators, we'll see later in the other module. So then on the top of the transmission line, you can see there is a static wire. So that is for support of the transmission line, transmission tower, for other safety purposes. Now coming to the other side, this is a three-phase line. You can see a three-phase line. There are three conductors. Okay, so three conductors. So it is a three-phase line, and each conductor is a bundled conductor. And here in specific, this is a double circuit three-phase transmission line. Double circuit three-phase transmission line. That means for each phase there are two conductors. Okay, so if we say this is A phase, B phase, C phase, so the A phase having the one more conductor, it is, let us say, A dash, B has B dash, C has C dash. That is how a double circuit three-phase transmission line. So this is just for an idea. So now once again recall the expressions, the derived expressions in the previous lectures, before going into the problems. For a single phase line, the inductance expression, inductance per conductor per meter, okay, 2 into 10 power minus 7 log base E dm by ds, okay, where dm is mutual GMD, ds is self GMD. So for a single phase line, that dm is nothing but spacing between the conductors simply, okay, the spacing between the two conductors, so which may be small dr, capital D. Next, ds is a self GMD. So for a single phase line, it is given by I hope you remember R dash 0.7788 into R. So 0.7788 into R. So That is for the single phase line. Next, a three phase line. First, about the single circuit three phase line. Single circuit three phase line inductance expression again for phase per meter length. So 2 into 10 power minus 7 log base E dm by ds, where dm is a mutual GMD for a single circuit three phase line. It is given by uh, point dm. I'm talking about dm. So it is given by cube root of, so that is dm is given by cube root of d1 d2 d3. D1 d2 d3 are the distances between the conductors. In the three phase line we have the three conductors, so the distance between them is it may be equal or different. So depending upon them, whatever it may be, the mutual GMD dm is calculated as like this: cube root of d1 d2 d3. Okay, distance between the three conductors. Okay, now DSC is given by like single phase transmission line, self GMD here also 0.7788 into R. Next to double circuit three phase line inductance per phase per meter and per phase per meter length is given by 2 into 10 power minus 7 dm by log base E dm by ds, where ds is cube root of ds1 ds2 ds3. Okay, self GMD ds is given by cube root of the ds1 ds2 ds3. What is ds1, what is ds2, ds1 is the self GMR of phase 1, self GMR of phase 1, self GMR of phase 2, the next one for phase 3. Next, okay, we'll see problem, then it will be more clear. Next to dm, mutual GMD is given by cube root of dm1 so exactly it is in terms of 1 2 3 or abc, depending upon the conductors how we take. If we represent conductors are abc, okay, or 1 2 3. So if the conductors are ABC, so mutual GMD means it talks about the distance between the phases, okay, not within the phase, right? So that is a mutual GMD. So between the phases, definitely, so DAB, DBC, cube root of DAB into DBC into DCA. Okay, so that is how DAB is a mutual GMD of first phase, A phase. Next, B phase, C phase. That is how it is. So we'll see a problem. First problem: find the inductance per phase per kilometer of double circuit three phase line. Shown in the figure here, the conductors are transposed. Okay, so it is given a double circuit three phase transmission line. The conductors are transposed and are of radius 0.75 centimeter each. The phase sequence is ABC. So they have given the conductor radius. Each conductor has the same radius 0.75 centimeter, and here look at the diagram, we can see here the conductors ABC conductors are there. Okay, and because it is mentioned double circuit, so double circuit, so means what, each phase having a, we have two conductors, so a has its a another conductor a dash, okay, and B has B dash and C has C dash. Okay, so this is position 1. So transposed line they mentioned. So in next position, the positions of this A B C will change. Okay, so that is what transposed line, right? Last lecture, that is what we have seen. So that is the second position. In third position, again changing the positions of the conductors, ABC conductors. So in this case, how to find the inductance? How to find the inductance? So here they ask inductance per phase per kilometer. Okay. We'll see at the end. Okay. Write that value, calculated inductance value per kilometer in terms of per kilometer. So first we have to recollect the expression for inductance in case of a three-phase double circuit line. Just now we have seen. So that is given by 2 into 10 power minus 7 log base E dm by ds. Log base E dm by ds. So here what is dm? What is dm? Total GMD, right? So dm is a mutual GMD total, right? Which is a total mutual GMD. So now that is given by this expression, right? Cube root of DAB, DBC, DCA. Okay. Then similarly DS also. Okay. So that is a DM, DS. Next, what is first we calculate? First we calculate DAB. Okay. DAB is a mutual GMD of the phase A. Okay. So here DAB is given by DAB is given by fourth root of DAB dash DA dash B DA dash B dash. That is DAB. Okay. So now we first, okay, that is DAB expression. Then similarly, if you write DBC, DCA also the same manner, right? So DBC is DBC bar, B bar C, DBC, B bar C bar. Okay, in the same manner, DCA also. Okay, so that is how mutual GMD of each phase is calculated. Okay, so this is for phase A, this is for phase B, this is for phase C. So here once get the correct values of this DAB, AB dash, okay, from the diagram given. So in the diagram, we see how to calculate DAB. See that this is how the diagram given. So the DAB is given by C. This is 4, this is 5.5. So DAB how to calculate from here to here? This is 4, right? So the remaining distance what? 1.5. 1.5 is going to divide exactly by 2, this side and this side. So 1.5 by 2, 1.5 by 2, how much it is? 0.75, right? So this length is 0.75. So we know this is 0.75 and this length is given 3 meters. So this distance is given by vector sum of this 4 meters and 0.75 meters, right? So that is what you can see here. Distance from A to B is given by square root of 3 square plus 0.75 square. This distance is 3, right? This distance is 3 given. Okay. Now, next similarly, distance DAB dash. In the same manner, DAB dash. Okay. Again the same manner from here to here. Okay. How to calculate this one DAB dash? So square root of 3 square plus this one. What is this one? 4 plus 0.75. Right? 4.75. So that is how DAB dash is calculated. Next. Okay. So then what? A dash B. A dash B is how much? Okay. Look at the diagram. Square root of 3 square. Okay. A dash B means this one, right? From here to here. It is given as square root of 3 square plus again 4.75 whole square. Next, A dash B dash. distance between A dash B dash is given by, we know that from this diagram, okay, that is given by how much? That is how much? 3, right? Distance A dash B dash, not 3, wait. So that is given by A dash B dash, right? So from here to here, so square root of 3 square plus 0.75 square. Okay, so that is how all these terms are calculated, distances. Then finally DAB is calculated. Okay, next at the same time DBC. Okay, D capital BC. Fourth root of D small bc. So look at the diagram again. Distance between B to C. So from the diagram again, it is given by square root of 0.75 square plus 3 square, right? So that is BC. Next BC dash. Okay. BC dash also the same manner from the diagram, B to C dash. Square root of 3 square plus 4.75 square. Okay. So that is how, okay, I hope you understood. That is how capital DAB, capital DBC, capital DCA are calculated. Then finally, to get the final DM, okay, total, okay, mutual GMD, cube root of cube root of capital DAB into capital DBC into capital DCA. So that is how DM calculated. Okay, then DS. DS is given by self GMD, okay, total self GMD, cube root of capital D DS1 into DS2 into capital D DS3. What is DS1? Here, DS1 is given by, okay, DS1 is given by self GMD of first phase. That means phase A, which is given by fourth root of DAA. Self GMD means self, we also call it a GMR, right? So within the phase, with distances between the conductors within the phase, right? It talks about self within the phase. So DAA, DA dash, A dash A dash A dash, right? So that is how DS1 is calculated. Okay, first DS1. Okay, with respect to phase A. Okay, so next, similarly, DS2. DS2 is DBB, BB dash, B dash B, B dash B dash. Next, DS3. DS3 also the same manner. Okay, with respect to C phase. CC, CC dash, C dash, C dash, C dash. Okay, now what is DAA? Suppose DS1 we are calculating. What is DAA? Radius of the A conductor, A strand, okay? So A filament. So that is given by simply the radius of the conductor, okay, but multiplied with 0.7788R. So that is what first thing, okay, DAA or DA dash A dash, okay, radius with respect to the radius of the conductor or strand filament, 0.7788 into R, that is given 0.75 centimeters. Okay, so but all distances in the diagram are given in the mentioned in meters. So we'll take this one also in centimeter, 0.584 into, okay, after doing this multiply with -2. Okay, then we will substitute in terms of only meters. Next, what is DAA dash? So how to know the distance between DAA dash? Again from the diagram, A is here, A dash is here, that is given by square root of 4 square plus, okay, what is this distance? 3 plus 3, 6 square. So square root of, okay, square root of those two gives the AA dash, okay. A dash A also the same, right? A dash is same as the A dash A. Okay, next. Similarly, okay, then substitute here. Finally, we get the DS1. Next, DS2 also. Okay, first calculate the what is DBB B dash B dash. Okay, with respect to the radius 0.7788 into 0.75 into 10 power minus 2. Then calculate this B dash and B dash B, which is directly from the diagram 5.5. Okay, then DSC also calculated in the same manner. Okay, then at last substitute in this, okay, and get the DS, okay, total self GMR. Okay, now finally to calculate the inductance of the line 2 into 10 power minus 7 into log base C dm by ds, right? So dm calculated, total dm calculated, total ds calculated. So substitute it here. Okay, so we'll see in the next slide what are the answers. So what I explained again here, it is clearly shown step by step. Okay, so you can see that here first ds1 ds2 calculation. Okay, then overall ds, total ds, then uh, dab dca, okay, calculation. Okay, so they have shown step by step, it is shown. Finally dm, total dm, okay, is calculated, which is obtained as 4.4 meters, and total ds is obtained as 0.195 meters. Now substitute it here. Okay, substitute it here in this expression. Okay, what is the answer? It is given as 6.23 into 10 power minus 7 meters. Okay, if we write that value in millihenries, 6.623 into 10 power minus 3 millihenries. But the answer, but the question they asked to calculate the inductance per kilometer. So finally, the value is written per kilometer. So 6.623 into 10 power minus 3 into 1000 will give us 0.623 millihenries. So finally, this is the answer. Okay, this is the answer for the given problem. There is one more problem. Determine the inductance of a single phase transmission line consisting of three conductors for 2 centimeter radii in the go conductor and 2 conductors of 4 centimeter radii in the return. Okay, as shown. Okay, it's look at that. What is a transmission line? Single phase line, right? Single phase transmission line. Okay, so but clearly mentioned there are 3 conductors in the go conductor. There are 3 conductors in the go conductor and 2 conductors in the return conductor. Okay, so look at the diagram, it will be more clear. So in the go conductor there are 3 conductors, we can see A, B, C, and in the return conductor, okay, there are only two, which are A dash and B dash conductors. Okay, so okay, and they mentioned it as first conductor is X, second return conductor is Y, and this is how the distances are given, and we know that how to solve this problem, like previous problem only. Only the thing is there is only 2 conductors in the return conductor. So then we need to do carefully little bit. So if we remember in my last lecture in composite conductors, inductance of composite conductor, there we have clearly explained GMD and GMR, mutual GMD, self GMD. Okay, with M and N, with N number of conductors in phase A, okay, M number of small m number of conductors in phase B. So then we have the expression, right? So in the numerator mnth root, in the denominator n square root. Okay, so that is how the expression. Okay, this is a mutual GM. This is a DM, right? In the power we have mnth root. Okay, in the self GMD we have nth square root. Okay, that's what I hope you remember. Okay, so now we need to calculate the inductance, right? We need to calculate the inductance of the line. Total inductance they asked. So because the conductors are number of subconductors are different here in the go conductor 3 and the return 2. So calculate each conductor. Okay, conductor X inductance first, then conductor Y inductance next, then add those. Okay, so here for the conductor A, how to calculate DM and DS. Okay, so we know for the nth conductor, for the conductor A, how many subconductors? 3, right? And 3. Okay, so then, so here this is a inductance expression they have shown in terms of log base 10. Okay, so the upper one is in terms of log base C. Okay, the down one, the next one is in terms of log base 10, and it is written in millihenries per kilometer, this expression. Okay, now here how to calculate DM and DS. Okay, DSX means with respect to conductor A, conductor X. Okay, which have the strands of 3. Okay, n value, small n is, remember, okay, small n 3 and small m 2. Okay, now so then dm is given by like this is the expression. So dm means distance between the phases. Okay, distance between the I mean conductors. Okay, not within the conductor, not within the conductor which has a subconductors. Okay, between the conductors. So dm for phase, for first conductor, conductor X we are writing. So in conductor X we have 3 conductors, right? What are those? A, B, C. Okay, so A, B, C. So what dm is written as okay, 1 by mnth root of, okay, of course we substitute here these two values. So distance between the conductors. So what are the conductors here? A, B, C. Okay, so I'm sorry, what are the conductors here? Yes, A, B, C. Okay, so see that distance between the conductors. So okay, on the other conductors are other side we have A dash B dash, right? So now for phase for first conductor, go conductor, dm is written as, okay, between the conductors, right? So that means what are the conductors? In the go conductor we have ABC, and the written conductor we have A dash B dash. So between the conductors means A, between A dash, A, B dash, like that. So that's why the terms are DA dash, D, A, B dash. Okay. Then this is uh, D, B, A with respect to next one, B, A. Okay. B bar. Next C, A dash, C, B bar. Okay. So this is for the first conductor. Okay, so then substitute the values from the diagram. Okay, like distances, it's directly given like previous problem. Consider those. Finally calculate the dm. Okay, next dsx. Dsx within the conductor, right? So within the conductor, so daa first, next dab, dac, right? Next dba, DBB, DBC, DCA, DCB, DCC, whole power 1 by n square. So here what is this AA, BB, CC, radius of the conductor multiplied with 0.7788, right? So that is what Okay, dA. Next, what is the remaining things from the diagram? Distances are given. We have to consider that and write the values. So finally, dm and dsx are calculated. Finally, inductance of the go conductor value, okay, substituted here. It is given as 0.4544 or 0.455 millihenries per kilometer. Mm, Next, inductance of the written conductor. What is a written conductor here? Y conductor, right? So, the expression of inductance. So, dm by dsy. So, what is dm? What is dsy? So, dsy is a self GMD of the conductor B, okay, which is given by, okay, which has only two conductors, right? So that's why, uh, what are those? DSY is given by, okay, D, D A dash, D A dash B. Hold on. Just two conductors, right? A dash, B dash. So D A dash, then A dash, B dash, B dash, A dash, B dash, B dash. Okay, whole power what? 1 by n square. N is how much? 2, right? So 1 by 4. So here you can see this is like this. But here what is the distance given? This distance is given 4, 4. I think that is 4, 4. So not that B dash, this is B dash A dash. And this is 0.7788 into R. Okay, these two. So what it will become? This square into whole power 1 by 4 means 2, okay, it comes only 2 gets cancelled, 1 by 2. That is how dsy is written. And then dm, what is dm? Yes, it's already there. So dm is it is same as the conductor A, mutual GMD for conductor. Written conductor also same as go conductor. Okay, so it is finally substituted and obtained. The value is given by 0.602 millihenry per kilometer. Millihenry per kilometer. Okay, now, now this is given by total inductance. Okay, as they asked in the problem, 1.057. Okay, so the answer for this problem is 1.057. So these are my references where I mentioned. Okay, this is a reference from the first test book. The next other problem is from that second test book. Okay, that's all for now. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.